In an earlier video, I introduced you to the idea of the angular velocity. If we have an object moving in a circle, then the angular velocity is the rate at which the angular position of the object changes. So let's say we have this object represented by the red dot moving in the circle. Let's say that in a time interval delta t, the object moves through an angle delta theta. If the angular velocity is constant, or in other words, if the angular position changes by equal amounts in equal time intervals, then we can say that the angular velocity of the object is change in angle over change in time. However, even if the angular velocity is not constant, in other words, even if the object is getting faster and slower and faster and slower, even if the angular velocity is not constant, we can still say that the average angular velocity for the process is the change in angle divided by the time interval. With that in mind, let's look at the process illustrated over here. I have a mouse running around a circle, but the mouse is not moving with a constant angular velocity. So here's what we have. At time equals 0, the mouse is at the reference line. At time equals 1 second, the angular position of the mouse with respect to the reference line is 20 degrees. At time equals 2 seconds, the angular position is 60 degrees. At time equals 3 seconds, the angular position is 120 degrees. And at time equals 4 seconds, the angular position is 200 degrees. We'd like to get an idea of what's going on. So we're going to apply this formula here, which allows us to calculate the average angular velocity of the mouse during a particular time interval. So let's start by just looking at that 1 second time interval between time equals 0 and time equals 1 second. What would be the average angular velocity of the mouse during that time interval? Well, we can apply the formula delta theta over delta t. So the change in angle here is 20 degrees, and the time interval is 1 second. So we can say that the average angular velocity of the mouse during that 1 second interval is 20 degrees per second. Here I'd like you to try something on your own. I'd like you to pause the video, and as the video is paused, work out the average angular velocity of the mouse during the time interval from 1 second to 2 seconds. Work out the average angular velocity of the mouse during the time interval from 2 seconds to 3 seconds, and work out the average angular velocity of the mouse during the time interval from 3 seconds to 4 seconds. So give that a shot and then rejoin the video. Okay, in this next 1 second time interval, the mouse goes from 20 degrees to 60 degrees, so the change in angle was 40 degrees. And it happened in 1 second, so the average angular velocity would be 40 degrees per second. In that next 1 second interval from 2 seconds to 3 seconds, the mouse went from 60 degrees to 120 degrees, so the change in angle was 60 degrees. It happened in 1 second, so the average angular velocity was 60 degrees per second. And in that last 1 second interval, 200 degrees minus 120 degrees gives us 80 degrees. So the average angular velocity for that second was 80 degrees per second. Let's summarize. In the first second of motion, 20 degrees per second. And in the next second, 40 degrees per second. Then 60 degrees per second. Then 80 degrees per second. Now we would like to try to describe in a sentence what's going on here. Why don't you try this on your own? See if you can write down a sentence which describes what's going on here using the concepts of angular velocity and the concept of time, but not using any other concepts from rotational kinematics. So give that a shot and then rejoin the video. You notice that in each 1 second interval, the angular velocity of the mouse is 20 degrees per second greater than it was in the previous 1 second interval. In other words, for every second that goes by, the angular velocity of the mouse increases by 20 degrees per second. Let me write that out. We can say that the angular velocity changes by 20 degrees per second in every 1 second time interval. What then would be the rate at which the angular velocity changes? We can say that the angular velocity changes at a rate of, here, why don't you try pausing the video and see if you can write down the rate at which the angular velocity changes. Okay, the angular velocity changes by 20 degrees per second in every 1 second time interval. We can say then that the angular velocity changes at a rate of 20 degrees per second, or in other words, the angular velocity changes at a rate of 20 degrees per second squared. Okay, so we have the idea that the angular velocity can change. The angular velocity can change at a specified rate. Let's give that rate a name. Let's call that the angular acceleration. Okay, so the angular acceleration, the symbol we use for that is the Greek letter alpha. The angular acceleration is defined as the rate at which the angular velocity changes. So in particular, we could say that the mouse in the figure here has an angular acceleration of 20 degrees per second, or 20 degrees per second squared. In the upcoming videos, we're going to further explore the idea of angular acceleration, and we're going to spend some time in particular talking about process for which the angular acceleration is a constant.